So first of all, I would like to thank organizers who give me a chance to present my work. So hi, I am Mohammad Kamran. So I am currently a postdoc at INF, and also I am collaborating with IFPU. So most of this work actually has been done during my first postdoc at Uppsala University. So my basically talk entitled basically proving the Mach power spectrum during the post-ionization era. So this is actually the artist impression of evolutionary history of our universe from Big Bang to present day. And as we know, universe from Big Bang to present day has passed through a number of phases like dark ages, cosmic dawn, epoch of reionization to present day. And we know that the two extreme phases which can be observed is basically cosmic microwave background and present day. Okay. So cosmic microwave background can be basically observed using, for example, Planck observations and Planck measurement, and present day can be observed using various galaxy redshift surveys. So we have well-known basically ideas of these two phases, but there are lots of missing pictures, and also these two phases basically provide clear picture of large-scale structure of our universe. So in these two extreme phases, we have lots of missing pictures of our universe. And most of the basically missing pictures lies in cosmic dawn epoch of reionization and post epoch of reionization. So Suman and Samir has already discussed about the CDEOR, and Suman has also discussed about something about post EOR. So I am not going into the details of all these era. So today I will mostly focus on the post ionization era, which is basically the redshift below 6 and up to 0. So and we know that during the post EOR basically, so IgM is completely ionized and H1 is basically located inside the bound objects, for example galaxies or halos. So and we basically can observe the H1 21 centimeter signal from the bound objects, not from the IgM, because IgM is mostly ionized. So what is the 21 centimeter signal? Basically 21 centimeter signal is nothing but the spin flip transition of the electron proton system in the ground state of the hydrogen atom, and when there is a basically spin flip from parallel to anti-parallel spin, so there will be emission of wavelength of 21 centimeter or frequency 420 megahertz. So and this wavelength will be redshifted as per the redshift, and we will observe basically the early universe as per the redshift. So in this work basically I have used 3 different simulations. So first I have used n-body simulations to populate basically the dark matter at different redshift, for example 531 I have shown here, and basically in this dark matter distribution I have found halos using FOF halo finder algorithm, and then I used halo catalogs to paint those halo catalogs with H1 using a very famous relation from Bagla et al. 2010. So this is basically empirical MH-MH1 relation, halo mass H1 mass relation. So here I have basically plotted on the top matter power spectrum and in the bottom H1 power spectrum. So here we can see that as we move from redshift 1 to 5, there is a basically increase in the power. Why? Because there is a clustering. So clustering is happening with the time. So power is also increasing with time. Okay, time is basically increasing, so power is increasing, or redshift is basically decreasing from high to low, power is increasing. But there is almost no evolution at various length scale in the H1 power spectrum, as we can see in the bottom panel. So why? Because first of all it will also depends on the MH-MH1 relation, because this MH-MH1 relation basically is kind of okay. If you basically increase halo mass, so H1 mass will increase, but after a certain threshold, for example 10 to the power 13 emission of halo mass, there will be no evolution in the H1, so H1 will be kind of constant. So halo mass is increasing after a certain halo mass, but H1 mass is not increasing. So here we have, and basically power spectrum mostly captures the high density regions, high density points, or basically over densities. So and here because the H1 content is kind of constant after a certain threshold in high halo mass, where basically the over density could be high, so H1 is kind of H1 is showing almost no evolution over the post TOR. For example, from redshift 5 to 1. So there is a kind of no evolution in H1. But of course, we know that there are basically a number of small mass halos, intermediate mass halos, for example, starting from 10 to the power 8 MSun to 10 to the power 13 MSun. Those halos exist, and inside those halos galaxies exist, and H1 reside inside the galaxies. So if halos are evolving, matters are evolving, so H1 could be evolving, right? But here we cannot see the H1 evolution in the H1 power spectrum, but there should be some evolution. So is there some method whether we can basically capture those evolution? So one answer could be lies in the terms of that, because H1 power spectrum, or basically standard power spectrum, mostly captures the Gaussian information, right? Or basically our information lies in basically in the Gaussian distribution. But there should be some non-Gaussian information in the distribution that is not captured by the H1 or basically standard power spectrum. But if we basically able to probe the non-linearity present in the distribution in some way, then there should be basically possibility of capturing the non-Gaussianity, and then through that connection in between non-linearity and non-Gaussianity could capture the evolution. Okay, so for this we have basically opted a relation which basically provide a relation between mark and density. So mark is nothing but is basically kind of transformation of the density distribution using this relation. So M is nothing but basically distribution, or basically kind of transformation of the density using this relation. So and this mark is basically defined as rho star plus 1 divided by rho star plus rho r to the power p. Okay. So if we just choose, for example, rho star 0 and p is 1, so mark would be just 1 by rho. Okay. So what does it mean? So if mark is just 1 by rho, means if density is low, then mark would be high. Okay. So it will basically, in case of, for example, positive p, low density will be upweighted and high density will be downweighted. This is one of the ways. If we choose, for example, negative p, so 1 by rho will be rho. So high density regions will be upweighted and low density regions will be downweighted. So what we are doing, we are basically kind of weighting our standard distribution using this mark developed by Martin White in 2016. And rho star here is the mark parameter, R is also resolution or basically smoothing length scale, and P is basically the exponent, okay, which will basically provide the amplitude of the mark, how basically how strongly we are kind of amplifying the basically upweighting or downweighting. So here you can see here the three different maps. In the left panel, basically I am showing here the standard density distribution, and in the middle panel I am showing the mark at p is equal to -2. So what it will basically provide with us. So it will basically upweight the high density regions. Here we can see that, and when we choose positive p, so here, so low density regions will be upweighted and high density regions will be downweighted. Okay, so this is the standard distribution. This is the mark distribution with negative p. High density regions are upweighted, and here low density regions are upweighted. Okay, yeah. So first I will basically show you the evolution of the mark power spectrum at two different smoothing scale. This is for 280 kiloparsec and 1.5 megaparsec, and I have chosen p positive, and which is 1. And we can choose rho star, for example, 0.1. This is basically one of the other mark parameter. So here we can see that with the positive p, low density regions are upweighted and high density regions are downweighted. And here basically we can clearly see the evolution of the H1 distribution, okay, at any of the smoothing length scale, right? And this evolution is directly reflected in the power spectrum, okay. So for example, when we are basically doing smoothing at 280 kiloparsec, here we are seeing basically a low power at low redshift, so power is kind of decreasing, And when we are considering R is equal to 1.54 megaparsec, which could be a characteristic length scale of the distribution, here we can see the power is kind of increasing. So basically, summary is kind of there is some evolution in the H1 distribution, which was not being probed by the standard power spectrum, but Mach power spectrum can do. Okay. And similarly, if we choose the negative peak, so only the density regions, or basically which are already at high density, will be upweighted, and low density region will be downweighted. So again, we can see the evolution in the power spectrum, right? So this means that both low density or intermediate density or high densities are evolving, okay, which is not being probed by the standard power spectrum. And also we have basically looked at how basically the Mach power spectrum evolves with the smoothing radius. So we have considered here, let's say, smoothing radius from, let's say, 280 kiloparsec to 280 kiloparsec to 4 megaparsec. And here we clearly see there is an evolution in the Mach power spectrum, for example, with the positive P. Okay, and here we have chosen the length scale K 0.16 MPC inverse, which basically probes the very large length scale. And also we can see here the evolution in the power spectrum, Mach power spectrum at P is equal to -2, which probes the high density regions, right. So now we can basically summarize that here the H1 density power spectrum basically shows almost no evolution over the entire redshift range in the post-TOR. But Mach H1 power spectrum can show some evolution over the entire redshift range in the post-TOR. So this is the summary of my talk. Thank you.
Thank you, Kamran. So there are several hand raised. So Atit.
Hi, Kamran. Actually, in observations, how will you do this marked statistics?
So this is actually a good question. So I was thinking in that direction. First, we should need to basically kind of so there could be two different ways. First, we should basically need to make a map, okay, original map, or we can do in in the original map we can basically choose some threshold, okay, and threshold should be chosen in a way that whether with that threshold we can basically probe that observations or not. Because if we choose very small threshold, then there should be possibility of basically not getting probed the Mach power spectrum. So rho star will be an important. Or if we are not making the map, which is also very difficult to make the maps, then we can basically kind of choose various number of thresholds, starting from, let's say, a very small value to large value, and then we have to basically see what is the effect on the Mach power spectrum, and then we need to match it with the basically theory. So of course, with the observation, it is difficult to do.
There's a small concern with the Mach power spectrum, and that shows up in your previous plot, which is you're essentially taking very small scale information
here
and pumping it up to larger scales.
Sorry, which plot? You are
Yeah,
this
that
plot?
plot. So you see that it's very sensitive to your smoothing scale. The next slide.
Okay. Yes.
So modeling becomes extremely difficult.
Modeling of what?
Up to what K? So suppose you want the power spectrum at K equal to 1. The fact that you seem to see information in the Mach power spectrum is actually coming from much higher K. So unless you are extremely certain about your simulation, for example, the power that you're seeing at K equal to 1 may not be reliable.
K
So have you thought
equal to 1 would be very small length scales.
K equal to 1 is already small, but you see your smoothing scale, you had some 200.
No, length scale I have fixed here, 0.16 MPC inverse.
Yes, but the information you're seeing here is coming from much smaller scales.
Yes.
Through the Mach.
Yes.
Okay.
Yeah. So see, I am doing smoothing on a very basically large map. Okay. So this R is basically related to the characteristic scales. This R is related to the characteristic scales. Okay. So what is actually characteristic scales of the distribution? But we are actually mapping the large scales because K is 0.16.
Yeah, Tirth has asked my question, but following up on that, how will you now, suppose you want to infer cosmology from your power spectrum, right? You showed that there's a d plus square dependence in the matter power spectrum, which is not so obvious in the H1 power spectrum because of the bias.
Yeah.
Now, if you put in your mark, how will you disentangle, let's say, this growth factor
Yes.
from the mark
Yes.
in the
Yeah, yeah.
context of observations?
Exactly. So I have no idea at this point because it's a completely first work, and we are basically kind of working on the other projects, and including the one that you are basically asking for, which is basically the bias.